So there's kind of two sources of videos. There's the stuff that gets automatically recorded by UNSW, that's the Echo 360 stuff. Has anyone tried to get to that and had no, or anyone had success of looking at the Echo 360 videos? Show of hands. Nobody. That's scary. Don't be afraid to tell me if you have. Has anybody tried to get to the Echo 360 videos and been unable? No good. No. Right. The what? Good. So there's that link there, that takes you straight to Moodle. Under the lectures I put some more direct links. They always told me that the Wi-Fi in these theatres was useless, and once you got enough people using it, it was futile, and it looks like it's going to be pretty futile to me. Anyway, on the lectures page there's a couple of links to either Andrew's lectures or my lectures. They go to Echo 360, you log into Moodle, and they should take you straight, once you've logged into Moodle, take you straight to the Echo page. If they're not, let me know and I'll look into it. As I say, I'm making my own videos. I stuffed up the first one and I've fixed it, and I'll upload it to YouTube today, and I'll put in a separate set of links to those. Alright, so let's take a look. Oh, I've got to start up my little, where's that called? Oh dear. I'm going to start up this thing. Why do I have a bad feeling? This is, oh, it did work good. Did it say okay? Yeah. Why is it not asking me to type my password? Thank you. Blah 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 blah. I should have done this before the lecture started, shouldn't I? Next time. I'll try. This size isn't great. I'll try the larger size is slightly annoying, and there's no intermediate size. Right, I'll try sticking with that for the time being, because the last time it was slightly annoying to keep scrolling. Right, so I discovered why I had that giant collection of files, some of which I didn't recognise, and in fact it's because this XFCE window manager looks at your desktop, and my desktop was covered in all this old stuff that had been sitting there since 2005 and things like that. So I cleaned it out, and now it's only got COMP1511 relevant stuff on it. I will make that directory open, so everything I do in the lecture is going to appear in that directory, and you can access that directory. Let me start up Window Manager. What was that beeping noise? Remember, true type fonts will give me something else. Oh yeah. Alright, that's my home directory. If I go into desktop, I will have just the stuff relevant to COMP1511. So that'll be sitting there. You can go and access it. In fact, I'll make it accessible right now. So, if you do the following command, you're not going to get very far. Wrong file name, wrong directory name. I'm moving between Macs and Linuxes. Right, if you do that, you won't have much luck. If you do this though, on one of the CSE servers, then you will have some luck. So you should be able to change in there, you can do all those, and there's a list of file names, okay, like most of which are .c files, but there are some notes which I was going to edit right now. Where's that gone? So if I go to here and look around the files, if you double click on a file, it will open the editor, and lo and behold, I get a totally different configuration to what I had in my office. How was that? Alright, good. Isn't that wonderful? Oh, I know why, because it's doing GVim. Silly me. But you've got to be quick on your feet, work out what the problem is, diagnose the problem, and come up with a remedy. Here's the remedy. Right, so when you want to edit a file, gedit is the command if you're doing things from the command line. The name of the file, but it's a good idea to use an ampersand, which will start your editor running in background, which basically means you can do things on this window and in the editor window at the same time. Alright, good. So now I finally got to the point. Well, only 17 minutes in. Alright, so Andrew's written a whole lot of lecture slides. We're not going to talk over the top of them a lot. We'd rather do demos and talk about things in the context of the demo. So you can have a look at a C program and I'll explain what's going on. Occasionally we'll talk about things on the slides, but not so much. But a couple of things that Andrew didn't have on his slides that I thought I might talk about. As you go through your course, you're going to come across the notion of what I've called computational objects, and as I was walking up to the lecture I thought maybe digital objects might have been a better name. But anyway, I'll stick with computational objects. So these things crop up in a whole lot of different contexts. The characteristics of digital objects are typically that they have a name, they have a value associated with them, and they have somewhere they live. Now, I've given you an example down here. A file is a nice example of a computational object. It's got a name. You know, all those .c files sitting in the directory had names. And it's got a value. In the case of a file, a value is what you see when you look at the file. If you actually open the file, you know, perhaps in gedit, and you look at it, that's its value, I would argue. The location of the file is the directory where the file lives. And it has various other properties that I will talk about right now, because I think I went pretty quickly over this stuff last time. So you can specify who's allowed to read your files and your directories or folders. It's a good idea to make sure you set that up correctly, because you don't want every man and his dog coming in and looking at your files. In particular, if you put your assignments in a directory that everyone else can read, and some nefarious student comes along and goes into your directory, takes the file, takes your assignment, and submits it themselves, they're going to get into trouble, but you're also going to get into trouble, because we'll have two copies of the same program submitted by different people, and we'll want to find out who actually wrote it. Now, since you wrote it, that's nice. So the other guy's going to get into, or other girl is going to get into trouble. But to avoid something like that, it's best to make sure that all of your directories are not readable by other people. Now, I think that the default behaviour of the system when you create a new directory is to make it not readable to anyone else. But I'll give you a way to check. So here we are with that ridiculous error message. Don't know why. Alright, so ls by itself just gives me a list of all the file names. So these are the names of all the computational objects in the current directory, which is home desktop. Okay? So the location of all those files is home desktop. The name, for example, there's a file called add.c. How do I see its contents? Good question. How do I see its contents? I gave you a possible solution before. Yep, I can use the editor. So if I go back, let's say I wanted to look at add.c, which is something we're going to look at later, I could say open, oh, that's not it's worth doing anyway, just for fun. Oh dear, I opened it, and hey, there's nothing there. Now I would have known that if I'd done an ls-l, which tells me all of the details of the file. And by the way, that I should point out, that one that appears is not part of the file contents, it's just something that the editor puts there. So you can see there's a slightly grey strip running down the side. That's put there by the editor. The contents of the file is what appears in this white part. Alright, so if we go back here, and I do ls-l, which I did last time, this is the thing that tells you all the properties of the files. Okay, on the right hand side we've got the name, add.c is the file that I just opened. So that's fine, that's its name. Over here we've got the owner, and my name appears twice because in Unix files have an owner, which is a user of the system. They also have a group. So if you wanted to share files, you probably won't be doing that so much this semester, but later on you probably want to. You can make groups and you can have the file accessible to the group. In any case, so there's a magic group called JAS, which has only one member, which is me, JAS. Okay, so that's why you get JAS appearing twice. That's the owner, that's the group. The next column that we got here tells you the size of the file. And now we've got a pretty good idea why we didn't see anything when we looked at add.c, because there's nothing actually in the file yet. I'll put something in later. There's a file called bits, and we can see that's actually quite large. Interesting. I wonder what's in it. I wouldn't recommend editing that, otherwise I should try it actually, just for fun. Let's do that. I don't know how gedit handles things like that, but we'll see. Good. It yells at you and says, couldn't open it for some reason. Why was it complaining? Gedit has not been able to detect the character encoding. Okay, so gedit is a program that operates on text files. That file called bits is not a text file, and I showed you last time how you can find out what kind of file it is. If I say file and give it a file name, it'll tell me what kind of file it is. And there's a lot of blah, 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 blah. So another thing I mentioned last time is a lot of the time computer systems will spew out lots of information. You've got to get used to filtering that information and just honing in on the interesting parts, and that's the really interesting part. So this thing called bits is an executable file. Okay, so it's not a text file, it's actually a program that's designed to run, so you can't edit it using a text editor. Let's see, what else we got? So you can see there's a file called hello.c, which is 105 characters long. Template.c, 128 characters long, blah, blah, blah. So there's lots of C files that are all fairly short, all less than 1,000 characters. All right, the other interesting property of all of these files is the stuff that's over here. So this tells you who's allowed to access the file. And it's divided into 3 lots of 3, plus 1 extra bit at the start. So the first 3 characters tell you what the owner is allowed to do with the file. The second 3 characters tell you what anyone in the group is allowed to do with the file. So this file happens to be in JAS group, so anyone in JAS group could read that file. And the third bits tell you who's allowed to, what anyone else on the system can do to the file. Okay? So, owner, group, and everyone else. So that file there, the file hello.c, the owner is allowed to read and write that file, R and W. The group is allowed to read the file, well there's only one person in the group, but anyone else on the system can read this file as well. Now, I've opened up this, I said before that I opened up this directory so you could access it. If you go into that directory, you won't be able to read any of the other files because they've got this kind of accessibility set up. They're read and write to me, they're not read and write to the group. There's nothing, the group can't do anything, and general public or everyone else on the system, i.e. you, can't do anything to this file. Okay. So if I wanted to make those files accessible to you, I'd have to tweak those bits, and the way I'm used to doing it is to use numbers. Don't worry about those numbers particularly. And if I say, I want to make, alright, let's start explaining this. Star.c basically means all of the .c files in the directory. Okay, I mentioned star last time is a way of expanding what files you're talking about. So change the mode of all of the C files in that directory to 644, and we'll show you what difference that makes. Okay, so now you can see that all of the .c files are still readable and writable to me, they're readable to the group, and they're now readable to you. Okay, so now you can see into that directory and you'll be able to look at those files. So, in general, and it's probably useful not to turn on public readability to your files. Okay, a simple way of doing that, if you're talking about plain files and not directories, is to, I'll just pick on one of them. So if I do that, let's have another look at ls-l. You can see that sum2a.c readable and writable to me, so I can make changes to it and look at it. Readable to the group, so anyone in the group can look at the file, but no one else, i.e. these last three bits here, everybody else has no permission to do anything to that file. They could see that the file exists, but they can't look at it and they can't modify it. One other thing that I should show you. So the directory that these files are contained in has a similar kind of set of permissions. So we've got the first three things are WX. For a plain text file, like all the .c files, RW basically means you can look at the file and you can edit the file. So if you've got those permissions, you can make changes to the file. For folders, and folders are identified by the fact that the first character here is D. Ugh, it's got the over it. So any directory will start with the letter D. The meaning of these modes is a little bit different for directories. If a directory is readable, it means you can do an ls on that directory. So you can look at what files are contained in the directory. If it's got a W, it means you can create files in the directory. So you can see from these first three, what does that tell you? Oh, sorry, executable, I should have said, means that you can do a CD into the directory. Okay? So that basically means I can CD into this directory, I can make files in the directory, and I can read, I can do an ls on the directory. If we look at what other people can do, and I'll just go straight to everybody. Everybody else has execute permission, so they should be able to CD into the directory. Someone want to try it and tell me if it works? Oh, the directory is. So if you're logged into one of the CSE servers, obviously if you're on your laptop and you're not SSH'd or something, you're not going to be be able to do much. But if you're logged into a CSV server, you should be able to do that command and get into the directory, and then if you type ls, you'd see all those files. Okay? So, in general, you'd want your directories to probably have a mode like 750. So if I do that, now anyone who tries to get into that directory won't be able to. Interesting question, if you're already in there, you're already in, can you do an ls now? No. So, it's gone away. Alright, so I'll put it back. So now it's got permission, everyone can go in, everyone can look at the files, and so you can see what all those files are. You can look at all the files that have read permission. If you try to look at that bits file, you're not going to get very far because it's executing. Yeah.
If I'm editing a file like that and you change permissions, can I just not save it?
You could save it somewhere else. Yeah, but you probably couldn't save it. Interesting question, I don't know. You have to try it around. Okay. Now, what was I all about? Let's go back to the editor. That's right. And I was looking at notes.c. Okay, so files are computational objects and they have various properties. And hopefully now, when you go into the lab and you're in a terminal window on your lab workstation, you'll understand what happens when you do CD and you do ls and things like that. Now there's another kind of extreme, wrong editor. You're going to see me typing a lot of weird stuff into this editor because it's not what I normally use. Okay. Another extremely important type of computational object are the variables that you define inside programs. Right? So, like any other computational object, a variable has a name, has a value, and it has a location. So, the name, you define the variable, so you decide on what the name should be. And we'll be talking about, useful names. So generally you want to give a variable a name that's meaningful in the context of the problem you're solving. So if my problem is to add up a bunch of numbers and compute their total, then that would be a useful variable name to start using. So I call variable total. So that's its name. All variables have a value, and they get that value by you assigning a value to it where the value is computed by an expression. So for example, if I was to put in my C program, total equals 50, that would be a very strange thing to do, and I executed that statement, the value of total would then be 50. Okay, so assignment sets the value of a variable. And you can set it as many times as you like while the program's running. And often, you'll set it in terms of a modification to its current value. So I might, if I was computing a total, I'm likely to be reading values and incrementally accumulating them into the total variable. So I might do something like this. So doesn't make sense if you think equals is mathematical equality. Well, it might make sense if value had to be 0. But what's happening here is that we're evaluating this expression, and C has expressions that look pretty much like regular maths. And to evaluate this expression, I look at the constituent components. So I see an object called total, I see another object called value. I take the values of each of these objects and I add them together. That'll give me a result, and then I take that result and I assign it to the variable total. So essentially I've added whatever's in value onto the variable called total. Is that all right? If you understand that, you're most of the way to understanding computing, I reckon. Alright, so the value, so talking about variables as computational objects, the name we've looked at, the value, whatever was last assigned to it. The location is where this fits. So all variables are going to be allocated a spot somewhere in the memory. You don't necessarily know where that is. You can actually find that out, but we won't be dealing with that aspect of variables until later in the course when we start talking about so-called pointers. So that, at the moment, we're just talking about variables in terms of their name and their value, and that's as much as we'll worry about them. Another important property of variables, however, is their type. So when you define a variable, you have to associate it with a type. And a type represents a set of values. And that set of values typically has a bunch of operations defined on it. So if, for example, I defined total, if I want total to be, if I'm adding up a bunch of integer values, then it would make sense to define total as an integer. Okay? So int is the C shorthand for integer. C uses a lot of shorthand stuff. You know, why write the whole word integer when you can just write int? Why write the whole phrase real number when you can just write double? Well, you could have just written real. So C does make a lot of shortcuts in what it calls things, so you've really got to get used to that kind of stuff. So when I make a declaration like that, it creates an object, but that object as yet has no useful value. Okay. So that's an interesting kind of thing if you think in terms of computational objects. What this declaration here does, and you can put that at the start of a C program, it creates an object, gives it a name, says how you should interpret its contents when it has some, but it doesn't actually give it any contents. If I wanted to be very safe, every time I declare a variable, I ought to assign it a sensible initial value. So something like that. And if you're thinking about what total does, that's an absolutely sensible value to assign total. So now what that'll do, it'll create a computational object called total. It'll say, all right, total is an object that can hold integer values, and it will assign the integer value 0 to that object. And then I can start using that object in my program. If you don't assign an initial value, C will foolishly perhaps let you start using the object with an initial junk value. So you've got no guarantee what the initial value is, it's just some random number. And then if you start using it, making assumptions about what you thought the initial value was, your computation is just going to produce junk. The C compiler is not bad at warning you if you've done something like that. So if you just start using a variable without assigning it an initial value, it will generally yell at you. But if you ignore what it says, you may end up with your program producing garbage. Okay, so that's variables. For the first few weeks, we're going to deal, and here I'm simplifying things a lot, there are more complex variables than just integers and floating point numbers. The type for floating point numbers in C, or the most useful type, is double. Why is it called double? So I can define a variable called x, which the style guide tells you not to do, but I'll do it lots in lectures because I can't be bothered typing long names because it takes too much time. So don't do what I do in lectures, do what the style guide tells you to do. And variables whose type is double can hold floating point values. So effectively, floating point values are effectively an approximation to real numbers. They can't represent all real numbers, but they can represent enough of them to be a useful approximation. In fact, the int data type is also an approximation. You can't represent all integer values. You can actually represent just a subset of the range of mathematical integer values. But you can represent everything within that range. In the case of doubles, you can represent a bunch of things along the real number line, but there are gaps between the actual values that you can represent, which is an interesting property of those kind of variables. Alright, now what did I want to do now? I guess we'll start playing around with C programs. That's what I wanted to do. I haven't even looked at the slides yet. That's good. What have I got here? I wonder if that's loaded. Oh, look, it's actually... right, so here we go. These are the links to the videos. I think these ones, if you click on those links, it'll take you to the Moodle front page. If you log into Moodle, it will then take you directly to the Echo page. Let me know if that's not true. Don't start looking at videos in here because that's going to completely clag up the Wi-Fi network. Oh, and something else. I'm going to go back to the thing. Yes, look, there's a poll currently running for you to tell me what's on my t-shirt. I give you some possible choices. Oh, interesting to see. So what I'm trying to assess here is how much culture there is in the room. Alright, so we talked about files, we've talked about variables. Next thing I wanted to talk about is compilation. So, as I showed you last time, blah blah blah.c in itself isn't an executable thing that you can run and get some results from. It's just a description of what you want such an executable thing to do. Description in an English-like language, although it's a lot more formal syntax than English. So we start out with a .c file. That's not executable. To make it executable, we need to run it through a compiler. So the compiler takes whatever the C file, I just call it xyz.c to say something with a .c suffix. If you don't put a .c suffix, I think the compiler will yell at you. So if you feed in a .c file, and conversely, if you pick an arbitrary file that says, hello, my name is Fred, and you call that blah.c, sure, you can try and feed it into GCC, but it won't like it very much. So what GCC tries to do, it looks at xyz.c, it tries to interpret that as a C program. So does the text in that file correspond to correct C syntax? And if it does, it will then take that and convert the meaning of that text into machine code, executable machine code. Okay, so there's a step involved here. I'm sure a lot of you have played with things like Python and so on. They work on a slightly different mechanism, or in fact, they kind of hide this process inside the Python interpreter. So you write a Python program, you load it into your Python interpreter, and you can just start using it. In the case of C, there's an extra step involved where you've got to take your C source code and explicitly convert it to an executable file. Now, I know a lot of you use IDEs, and they hide this stuff as well. But we want you to have a deep understanding of what's going on here, and that's why we use command line so that you can see all the steps that are happening when a program goes from being a piece of text to something that can actually execute. So if you feed xyz.c into the GCC compiler, it will, if the program looks correct, it will produce a file called a.out, which is an executable file which you can then run, and you can get it to do what the C program says and produce some results. If the xyz.c file is syntactically invalid, the C compiler will print error messages and it won't produce one of these. Okay? If the C compiler produces an a.out file, a lot of first year students think, oh beauty, my job is done, I've got an executable. No. Because you may produce an executable that doesn't do what you thought it was going to do. So there's definitely extra stages involved here of checking whether your program actually does what you thought it was going to do. So GCC will take an XYZ file and produce an a.out. Let's have a look at an example of that. If we go back here, that didn't work, did it? So, I think this one's like the one I did last time. Alright? So a program that simply prints out the word hello on a line by itself. Right, so this has a bunch of structures in it that I think I talked about a little bit last time, but I'll talk about it again just in case you missed something. These first two lines up here are comments. They're not actually something that the C program, that GCC is going to convert into anything executable. They're there primarily for documentation so that anyone reading this code knows what it's supposed to do and who wrote it. You can actually put anything you like in there, but by convention what we normally put is what's the purpose of the program and who wrote it. And it's important. One reason for putting who wrote it at the top is if it gets submitted by someone else, we know who wrote it. It wasn't that person. And there have been some students who have been dumb enough in the past, take someone else's code, leave the other student's name at the top, and then submit the program. Bit of a giveaway. Right, so the first two lines are comments. Comments are really important. Make sure you put sufficient comments. That's an interesting question in itself. How many comments are enough? A comment on every line of code is probably too much. A comment on a chunk of 10 lines of code that's performing a particular task, I reckon, is about right. So this line 4, basically what we're saying here is that I intend to use some of the libraries, collections of C functions that the system provides. I'm using a particular library for doing input and output. It happens to be called stdio, standard IO library. And the .h is the conventional suffix that we use on C header files. So standard IO.h is actually just a file that contains a list of function headers, if you like, function signatures, that say what each of these functions in standard IO, or how you, essentially, what arguments do you pass in, what results are you going to get back. So that just makes a whole lot of definitions, and then I can start using these functions down here, and the C compiler won't complain. What are you talking about? I've never heard of printf. I can show you exactly what happens if you don't put a hash include. Let's save. So we've got hello.c. So see, by putting that // at the start, I've turned that into a comment, which means the C compiler isn't going to do anything with it, i.e. it's not going to read in the definitions and make them available to the program. So if I go out here, where are we? No. Okay, so it tells me in extremely long words, that's probably the important bit. It's saying you've got a function that you're trying to use, but you haven't told me exactly how to use that function. So essentially what it's saying there is, I don't know what this printf function is, or at least I don't know what its input should be and what outputs it's going to give. So as soon as I put that hash include back, basically what that does, import all of the stuff from standard IO, and then when I do the compilation, it's not going to complain anymore. So it'll actually find printf and include it in the file. So, include it in the executable. Alright, so if I look, you can see now I've got a file called a.out. That's the default name that the C compiler will produce. I can prove that it's the one I just created by looking at the file time. So March the 1st, 1150, which is right now. So that's when that a.out file was created. So now I've got an executable file which has one silly task to display the word hello. Executing that file, essentially you type the name of the executable file. So in theory, I should be able to type a.out and it will run the program. But, due to some bad behavior in the past, we don't by default execute anything sitting in the current directory. So if you want to execute an executable file that's in the current directory, you've got to be explicit about that, and it turns out that the current directory's name is actually dot. So if I say ls dot, it will tell me the contents of the current directory. If I want to execute a.out in the current directory, I say ./a.out, and then that runs the program and it says hello. If you're insane, you can change the behavior. Oh, by the way, I should have mentioned this thing that I'm talking to is called the Unix shell, and it has a lot of environment information associated with it, blah, blah, blah. You can see that there. One of the things that you can talk about here is where you want to look for executable commands. So what I've set up is that if I type the name of a command, what the shell's going to do, it's going to look in this particular directory here and say, is there a file that I can execute with the name I just typed in that directory? And if there is, it will execute it. If there's not, it'll go to this directory. If it's not, it'll go to this directory, and so on and so on. And it will run through all of the directories. If it doesn't find a file with the particular name I typed in any of those directories, you get that message. And you'll get that message, you know, if you do something silly like type ls by mistake, you type lls, okay? So that's what that means. It means basically, generally, means you type the name wrong. So one important thing to see up here, so this is just a list of directories. Directories are separated by colons. You can see that dot, the current directory, doesn't appear in that list. If I was a little bit mad, then I could potentially do something like, and I could put the current directory in my path, and then, hopefully, if I did that right, I can just type a.out. But the reason we don't do that is if you change into someone else's directory, they may have put a suspect program in there with a name like ls, and if you go to their directory, you may end up executing their version of ls, which could be some kind of hacking program that says, enter your password and I will display all of the contents of the directory. Now, anyone who types their password to something like that is completely mad, but that's the kind of thing that happens if you put dot in your path. So we leave it out and we force you to type /. So just be explicit about where the executable is located. Another way I could run this program is I could say, in the directory homejas desktop, there's an executable called a.out. Please execute. So, if you like, this thing has a number of different No, well, the name of the file is a.out, but you can refer to its location in a number of ways. If you already happen to be in this directory, you can use dot. If you're somewhere else, you can type the complete path all the way to the a.out file. Alright, let me see, what are we up to? 11:56, that's not. Alright, so anyway, I'll have a break now and I'll try to make the air conditioner work better. And after the break, we'll talk about more interesting C programs that actually use variables for useful tasks.